Hi guys, welcome to the channel. So in the previous video we were discussing about the types of electronic transitions. So we will continue with that topic, and today we will now discuss with the second type of transition, that is N to sigma star transition. So these type of transitions are observed in saturated compounds, containing heteroatom with lone pair of electrons. So for example, the saturated ketones, halides, amines, ethers, etc. These all will come into the category of heteroatoms having the lone pair of electrons. So we will write that down. Saturated ketones, halides. Halides will be fluorine, chlorine, bromine, iodine. Halides, amine, amines and ethers, etc. So they require very less energy as compared to the sigma to sigma star transitions. So for example, we will be having some kind of a heteroatom, suppose any halide. So these will be showing the N to sigma star transitions. So these will be having the lone pair of electrons as well. So if we now want to compare between the halides, now compare. Suppose we have chlorine, and here we have iodine, right? Here we have chlorine and here we have iodine. Now we want to compare the N to sigma star transition taking place here and taking place here. Now if we compare this Cl with this iodine, so this Cl is more electronegative, right? As compared to iodine, it is more electronegative, right? If we compare if we look at the electronegativity of the elements, then fluorine is highly electronegative, followed by oxygen, then nitrogen, then chlorine, right? So iodine has very less electronegativity, it has a very big size as well. So in general, I'm writing it down that fluorine has highest electronegativity in the periodic table, followed by oxygen, then nitrogen, then chlorine. These are very electronegative elements. Now, because chlorine is more electronegative than the iodine, so chlorine will hold the electrons more strongly, right? Chlorine will hold all the electrons more strongly towards itself, so more energy will be required for the excitation of those electrons. So here energy required will be more. Energy required will be more. Why? Because it is electronegative, it will hold its electrons very strongly, so more energy will be required to take out those electrons for the excitation. So because it requires more energy, that means it requires less wavelength, right? Because E is inversely proportional to lambda. Why? Because E is equals to hc by lambda. More energy means less wavelength. So because high energy is required, so therefore less wavelength will be required. And in comparison, if we look at iodine, it is very less electronegative. So because chlorine is more electronegative, energy required is high. So here comparatively energy required is low. Comparatively energy required is low and wavelength required will be high as compared to chlorine one. So in this case, wavelength will be lower in case of this compound and wavelength will be higher in case of this compound for N2 sigma star transitions. Now there are certain exceptions in the case of hydrogen bonding that we will discuss in the solvent effects, the topic that is solvent effects. So we will discuss that exception as well. Now we will move on to the third type of transition, that is pi to pi star transition. Now in these type of transitions we will be having unsaturated compounds. So pi to pi star transitions will be shown by the unsaturated compounds. Now one thing to understand is that we need not wait. We need not learn these things like N2 sigma star is observed in saturated compounds containing heteroatoms with lone pair and pi to pi star requires unsaturated compounds. The type of transition itself will tell you the type of atoms which will be present in a particular compound. For example, in N2 sigma star transitions, you see we have N. N means non-bonding. So non-bonding electrons will be present so that we could see the N to sigma star transitions. If we want the non-bonding electron, that means we need the lone pair of electrons. So lone pair of electrons are found where? In saturated ketones, halides, amines, ethers, etc. So these will be the type of compounds which will show N to sigma star transitions. Now if we are talking about the pi to pi star transitions, so pi electrons should be there so that they could go to pi star orbital, right? So pi electrons will be where pi bond is there. Pi bonds are in unsaturated compounds, right? Now these will be observed in unsaturated compounds. For example, compounds containing double bond, triple bond, or maybe the aromatic compounds, right? The aromatic rings. So they require very less amount of energy. Very less energy is required. So less energy means high wavelength. High wavelength will be required. So examples will be what? Alkenes, alkynes, carbonyls, compounds, cyanide, azo compounds, etc. So all of those which will be having the unsaturation, double bond or triple bond present, those will show the pi to pi star transition. Now we will discuss about the overall energy profiling very shortly in this video or maybe in the next video. So now we will move on to the N to pi star transition. So now we have N to pi star transitions. Now what type of compounds we need, that will be told by the transition itself. Suppose we have the pi star orbital. So if pi star is there, definitely pi is also going to be there, right? If pi is there, that means we need the unsaturation, that means double bond or triple bond. Now we have the N. N means non-bonding. Non-bonding means we need the lone pair. Lone pair means we need the hetero atom. So these are observed in compounds having unsaturation and lone pair. For example, unsaturated aldehydes or ketones. So if we look at this compound, suppose we have some groups R and R dash, and we have this oxygen doubly bonded, and this one is having the lone pair. So this is having lone pair and this is having the unsaturation as well. So they are going to show the N to pi star transitions. So they require very less amount of energy for their transition. We will see that in the energy profiling. So these type of compounds show both type of transition, that is pi to pi star also and N to pi star also. So both of these type of transitions will be shown by these type of compounds which are having some lone pair and the unsaturation. So this is about the N to pi star transition. Also in such compound, N to pi star transition, it is nearly at 290 millimicron or nanometer, and pi to pi star is at around 180 millimicron or nanometer. So very less amount of energy is required for their transition. Now in the next video we will start with the energy profiling. That means which types of transition need more energy and which type of transition need less energy, and so which type of transition need more wavelength and which type of transition need less wavelength. So we will discuss that in the energy profiling, which will be the topic of next video. So I hope till now everything is clear to all of you guys. After doing that, we will see after the energy profiling we will see about the symmetry as well, that is gerade ungerade, that will be inside that topic only. After that we will go to the formation of absorption bands. So I hope till now everything is clear to you guys, and this video was at least a bit helpful for all of you. So far that's it for this video. Thank you so much for watching.